So finally, let's talk about George Lindsay, our final sabermetrician that we're covering in Sabermetrics 101. And here's a photo of George Lindsay as he's enlisting in the Royal Canadian Military right after graduating from the University of Toronto. He was born in 1920, and his degree at the University of Toronto was in math and physics. And he was so talented and smart that he moved over to Britain to work on the radar systems that Britain was implementing. This was a secret system they were working on to combat the Germans during the late stages of World War II. After that, he got his PhD in Cambridge in the Cavendish Laboratory. This is where he met his wife. His wife also got her PhD from the Cavendish Lab. And for those of you who know biology, have probably heard of this before. This is the lab that Watson and Crick roamed in the early 1950s as they were discovering the structure of DNA. And this is well described in the book by James Watson called The Double Helix, a great history of the lab and what they did and discovered there. But interestingly, George Lindsay and his wife were in the same laboratory. He got his PhD in 1950. His wife got hers in 1951. And after 1950, he moved back to Canada to work with the same man he worked with during the war effort. And in his capacity in the Canadian National Defense System, he spent decades working as a nuclear scientist and working for nuclear disarmament within the Canadian National Defense System. And as a result of this, his efforts in the lab and working for Canada, he became an officer of the Order of Canada. That's what the OC is after his name. So he earned that in 1989. And there's this great quote from his obituary that epitomizes again what we're trying to do here in Sabermetrics 101. We're trying to explain this approach to the world that George Lindsay did throughout his career. So from his obituary in 2011, no matter the problem, he always proceeded in the same way. Collect the data, analyze the statistics, reach a solution, and implement it. That's because he had an empirical approach to life both at work and home. So again, this is something we've tried to emphasize in this course for our students and our learners. This idea that we collect data, we get data, and we start looking at it. We start trying to understand it. We start analyzing it. We start using statistics that we know of to better understand it. And that's what George Lindsay did with his work in nuclear physics, with his work in baseball. So we're going to cover his work in baseball, but he was quite an interesting man, a Renaissance man who did many different things, but took his passion for baseball and wrote 3 separate papers that are very important, actually, in the history of sabermetrics. This is a very prominent sabermetrician, and he published all of his work over 50 years ago. So the first baseball paper was published in 1959, and it was titled Statistical Data Useful for the Operation of a Baseball Team. And his basic thesis we've heard before. This comes direct from work from F.C. Lane when he published in 1916 a criticism of batting average. And quotes from Lindsay's paper where it's the most significant statistic in general use in baseball. And the criticism obviously is no distinction is made between a very useful hit and a lucky hit not ultimately aiding the team. A criticism of batting average is where he starts out this paper. But the main question in the paper is, can batting average be used to predict future performance? In other words, is batting average some kind of skill that's consistent for players over their careers? And can we use someone's batting average to say, well, this player will hit this batting average again? He did some analysis to try to understand the consistency of batting average over time. This is very similar to the analyses we talked about in the statistics section of Module 6 when we looked at small sample size and the work of Russell Carlton. His technique was different, but Lindsay does similar things trying to answer a similar question. Can batting average be used to predict future performance? So the main question again of the paper is, can batting average be used to predict future performance? And as Lindsay started thinking about this, he starts identifying many situations that impact batting average and the analytics of batting average. Park effects, league effects, day-night effects, clutch hitting effects, different skills of the pitchers that may impact batting average as well. And because of this, he just thinks there's too many situations to test all the different impacts on batting average. That to do this correctly, you need to look at each of these situations independently to try to find the effects during these situations. He does do one analysis, though, and he tested this easy situational difference. He looked at over 400 games, analyzing over 6,000 at-bats of right-handed batter versus right-handed pitcher, or left-handed versus left-handed. That batting average was 231, and when the right-handed batter faced the lefty pitcher, or vice versa, the batting average was 263. And the p-value of this test here was less than 0.001, which means there was a 1 in 1,000 probability that the result he got of this difference, the difference here between 263 and 231, the probability that that difference was just by chance was 1 in 1,000. The p-value here, and whenever you see it again, the p-value is defined as the probability of a false positive. A positive here meaning a positive result where you've rejected your null hypothesis that you've set up in your test. So the null hypothesis is that the right-handed pitcher, right-handed batter is the same as the right-handed batter versus the left-handed pitcher, that those two situations are the same. If that's your null hypothesis, what you're showing is that they're different. In other words, there is a difference between the two. And the probability that you see this positive difference, but it's actually untrue or false, is 1 in 1,000. So that's what the p less than 0.001 means, and what the p-value means. The p-value being so small, in other words, means it's highly significant. It's statistically significant. So you'll see this again as you take future stats classes, as you try to cover these errors you might get in your experimental design. So remember, the main question of the paper was, can batting average be used to predict future performance? And Lindsay concludes in this paper that it cannot be. There's too much sampling error in batting average. There's too much noise in the measure of batting average to have batting average be a statistically significant predictor for the next year, the next batting average. Batting average as some measure of a true talent is not the way to go. It's a wrong measure of some true talent. And this was one of his ideas at the start. Batting average wasn't a great measure of hitting performance. It misses some key factors about what hitting performance actually is. So it makes sense in a way that you can't use it to get at the measure of true talent that's going to predict the true talent in the future. In other words, what a player actually can do as a hitter. We'll stop here before we analyze further some other data covered in the first paper by Lindsay from from 1959.